Good morning, everybody. Welcome to Tuesday morning. Yeah, it's Tuesday. I put out the garbage last night. Tuesday morning at Chem 1211 with your host, me, Dr. White. As you should have seen by now, I put out an announcement that I have to revamp this whole course in terms of tests and uh, how I give them. One of your colleagues raised issues with my dean and the chairman, and because of that, I'll be rewriting how we do tests. And the way I think I'll do it is I'll be having a number of quizzes which we will take online. You still will have to take two tests and a final at the COD testing center, and this is a guidance I got from more than guidance from the chairperson of the chemistry department. So I thought I had it all worked out. Obviously, I didn't. Originally, I had thought this being a net course, everything would be online, and that was shot down. So sometime, let's see, today's Tuesday, by Thursday, I will have it figured out. I almost have it now, but I want to let it sit a day and look at it so I don't have to go back and change things. If you already took test number one, I'll work out something with you on that. As of now, if you have not taken test number one, don't go to the testing center. I have them cancel that because I'll be replacing a number of the tests with, and Jasmine, that's correct. I'm not sure what it will be. The way I'm thinking, and I'll stress this thinking, there'll be 6 quizzes, 2 tests, and a final. And I'll have some formula of dropping the first test or quizzes or combination. I haven't figured that out yet. I'm trying to work it out such that none of you are harmed by what occurred. I had no hand in it, but I'll straighten it out and we'll get things going. And like I said, you'll need to take 2 tests, not test number one I was supposed to give this week, but there'll be 2 tests and the final. You'll have to take a COD, and then there'll be a number of quizzes you'll take online via Blackboard, where you'll download something, take the quiz, and then upload it, and I'll grade it. And let's move forward. Let me close this. All right, today's game plan. All right, I'm going to talk about chapter 5, then get into chapter 10 for a little while. We'll take a break, and then we'll do our exciting lab. You know, this lab kit looks like it's pretty good. Now, one thing I should mention, because a couple of you have already asked, if you have not received your lab kit yet, and that happens, it's happened in the past, what I will do is extend the window for the labs where you didn't have the kit. Let me know by email, and also send me some sort of confirmation from the company when it's being shipped, or the fact that it's going to be late, or when you might be expecting to get that. And anybody who doesn't have the kit, I'll do that. So once again, we'll do chapter 5, finish that, do some chapter 10, and then we'll do the lab. All right, let's get to work. All right, thumbs up, people. Do you see polyatomic ions on your screen? Thank you. All right, we're talking yesterday, I was, about polyatomic ions. Poly means many, atomic atoms, and they're ions, which means they have a charge. In chapter 10, I'll talk more about what ions are. And it just sort of tells you about what I think of the book when they talk about polyatomic ions. Well, we really haven't had an in-depth discussion of what ions are, but we will. and I'm trying to make the best of this situation, which is why we're jumping around. So a polyatomic ions are a group of atoms that have acquired electrical charge, which is being shared among the atoms of a group. So you have a number of atoms combined together to form a group that has a charge on it. Now, when you name these, the most common ends with ATE. It says you will need to memorize the key. There are a couple I'd like you to know that's on the next table. And let's go to the next table. Now, here are some, let me size this properly. Here's some key polyatomic ions that you should be familiar with. And the ones on here you should know. You should know nitrate is NO3 minus. Nitrite is NO2 minus. Now, these are two polyatomic ions combined with a cation that have been used as preservatives in various meats, such as bacon, hot dogs, bologna, salami. And there's some concern, I don't know how much evidence there is, that these can cause serious medical problems. I, for one, have been eating salami and bologna all my life and hot dogs. Well, I've given up hot dogs mainly because there's better stuff I found than hot dogs at this point in my life. But when I was younger, I ate a lot of hot dogs, and look what it did to me. Oh, yeah, it is dangerous. But anyways, those are two. We have ammonium sulfate you should be familiar with. SO4 minus 2 or 2 minus. And bisulfate. Oh, I'll tell you what, let's skip bisulfate. You should know carbonate, bicarbonate, and later on, the last two will later in the semester talk about heavily hydronium hydroxide. So you should know these names and the structure. And I'll talk more about it after we finish next chapter. We'll come back to this when it makes more sense. Now, in the book, there's a thing naming acids, oxyacids, and formula mass. We'll cover this later in the semester. Again, problem with the book, they cover things in my mind out of order, where you don't really know about an acid yet until you learn about what are acids and bases, which is a later chapter in the book. So why learn how to name them if you have no idea what they are? And with that, we've finished chapter 5. And you know what that means? It's new chapter time. And let's go right to it. That new chapter is chapter 10. Again, follow along in the syllabus. It's listed. And chapter 10 deals with chemical bonding. We talked about what is a chemical bond. It's the force that holds atoms together in molecules. And there are two types of chemical bonds. As I've already talked about this, but I'll say it again. You should know what is an ionic bond. And that's the transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. One thing I should point out for chapter 10, I'm going to be adding some major pertinent material from the slides that are not in the chapter. So in other words, major additions of pertinent material for this chapter's slides has been made by me, your instructor. All right, so when we talk about chemical bonding, one type is the ionic bond. That's the transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. And this you should know, because if I ask on a test or quiz, whatever I'm going to come up with, what's an ionic bond? You should know this. Now, the other type of chemical bond is a covalent bond. And again, I'll be subtle. Know this. And that's the sharing, results from the sharing of one or more pairs of electrons between atoms. So covalent bond, you're sharing pairs of electrons. I don't know where I came up with this years ago, like holding hands. Here's an electron, here's an electron. We're sharing them. And by sharing them, you clamp two things together in a chemical bond called a covalent bond. So ionic bond is transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. And covalent bond results from the sharing of one or more pairs of electrons between atoms. Remember, pair means two. Pair means two. Now, we talked about this briefly, and now let's get into it. The most important electrons when you're talking about chemical bonds, whether ionic or covalent, are the valence electrons. Remember, I asked you to learn that the valence electrons are the outermost electrons of an atom. And how do we show this? Well, there's a convenient way to represent valence electrons. And your book calls it electron dot symbols, but to honor the chemist who invented this, they're also called Lewis structures or Lewis dot structures. So what are Lewis dot structures? Well, first of all, remember valence electrons. Ooh, I've got to open up a periodic table. Everybody see your friendly neighborhood periodic table? And this will be available for you when you take the quizzes online. And if we look at the top of each column, the number there, thank you, Jasmine, the number there, the top of these columns tell you how many valence electrons. An example, oxygen, you see on the top of the column, 6, and therefore it has 6 valence electrons. And you're not going to have to memorize this because you'll have the periodic table. Now, as I just pointed out, the valence electrons, the number is the same. The number on top of a column is the same as the number of valence electrons. And the valence electron, number of valence electrons for the representative group in a column, or group is a column, is the same as the Roman numeral or Arabic number, periodic table group number. Now, remember, the maximum number of valence electrons for any element is 8. Well, how do you show this? Use a Lewis structure. Now, how do you do Lewis structures? It consists of a element symbol, chemical symbol, with one dot for each valence electron. Now, it turns out you ignored D and F. It's only the S and P electrons. And the important thing is always place one electron on one side of the element symbol before putting a second electron on any side. So you always put one on each side before you double up. Oh, okay, it's Lewis structure practice time. Let's do these. Let's do the Lewis structure for sodium. And sometime in the future, on whatever type of vehicle I give you to determine, have you learned this, like a quiz or a test, it will say, and one might be sodium. And you have to know the chemical structure for sodium is Na. Next, Lewis structure shows valence electrons. And if we go to our friendly neighborhood periodic table, here's sodium. How many valence electrons does sodium have? You look at the top, not the 11. That's how many electrons and protons. We're talking about valence electrons, the outermost electrons of an atom. And you look on top and you see I have the number 1. So there's one valence electron. How do we show that? A dot. Now you could have put it there. You could have put it there. You could have put it there. And you could have put it right there. All those would be correct on a test. All right, let's do B, magnesium. You have to know the chemical structure for magnesium. Chemical symbol for magnesium is Mg. And if we go to our periodic table, here's magnesium, second column. How many valence electrons does it have? You look at the top and you say, oh, 2. So now I have 2 valence electrons. I'll write it here. 2 valence electrons. Therefore, I put a dot on each side. This is a possibility. This would be a possibility. Now, you never pair up until each side has a dot. This would be wrong. No, because you don't pair up until each side has a dot. And you only pair up once each side has a dot. So let's move on to oxygen. And now you need to know the chemical symbol, first of all, for oxygen is O. And then I'm going to let you do this on your own. First of all, how many valence electrons does oxygen have? And hopefully you all pick 6, because that's the number on top here. So we have 6 valence electrons. I'm going to let you draw the Lewis structure, and then I will. And when you're done, give me a thumbs up. Well, I see almost everybody's done. All right, let's do it. We have 6 valence electrons. So I'm going to start putting them in. I'll put 1, 2, 3, 4. Put 1 on each side before you double up. Now we have 2 more to go. So 2 of the sides will now have 2 dots. Now, organic chemists, for a reason I don't know, I sort of know, usually do it this way. This would be one answer. 2, 4, 6. 1 on each side before double up. You could have also done this, which would have been correct also. And there are others, as long as 2 sides has 2 dots and 2 sides have 1 dot. And by the way, there's never more than 2 dots on a side. Oh, let's do one more. Ooh, I see my favorite. And you would be asked, do the valence Lewis structure for argon. Now, I'll help you out today. Argon, the chemical symbol is Ar. And the first thing you have to do is look at the periodic table and find out how many valence electrons argon has. And if we look right here, Ar, inert gas, no, 18 is number of electrons and protons. That's not the valence electrons. The valence electrons are the outermost electrons, which you find by going to the top. And as I said the other day, I guess yesterday, I found out a couple years ago that they were no longer teaching Roman numerals in school. When I was in school, I think first or second grade, I learned this VII, VIII is the Roman numeral for 8. V is 5 and each I is 1. 5 plus 3, 8. But since students didn't know that, I wrote the number 8 on top. So argon has 8 valence electrons. And since I want to share the fun, why don't you draw the Lewis structure for argon? Now that you know there are 8 valence electrons. Your turn to have fun. And when you're done, give me a thumbs up, please. Remember, 1 on each side, and then you start doubling up. Well, one person's done. Another one. All right, let's start. How do we do that? Well, we have 8 valence electrons. We found that from the periodic table. So I'm going to start on one side. I'll start here. It doesn't matter. 1, 2, 3, 4. 1 on each side before you double up. Well, if I've done 4 and I have 8, I have 4 more to do. So this will be 5, 6, 7, 8. And that's the Lewis structure for argon. Each side has 2 dots or 2 valence electrons. And this is a skill you should know how to do. I'll say that again. This is a skill you should know how to do. Now, I'm going to turn the switch off, meaning I'll never ask you what is the octet rule, but octet comes from the number 8, like a quartet is 4 people in a string band, say octet would be 8, and there's an octet rule. And the octet rule is in both ionic and covalent compounds, atoms tend to acquire the electron configuration of the nearest noble gas. Now, what does this mean? Well, it means it has the same number of valence electrons as the nearest noble gas, which is 8, which is why they call it the octet rule. If we look at our periodic table, the column all the way on the right here are the inert, well, did I have inert? I think I had an old slide, are the noble gases. And therefore, we look on top, it has 8 valence electrons, and all the rest of the atoms want to have 8 valence electrons because it's very stable. And stable makes atoms happy. I bet you didn't know atoms have feelings. They don't, but it sounds good. So I have noble gases here. No, I had it right. My mind had it wrong. So when we talk about valence electrons, those are the outermost electrons. Certain arrangements are the most stable. In other words, they don't just spontaneously change. And that's a good thing. And the most stable arrangement is NS2 NP6, where N is the shell number. That can be 1, 2, 3, or 4. And 2 plus 6, 8 valence electrons, which is what the noble gases have. And they used to be called inert gases because for a long time, in fact, through my undergrad, grad school, I think into working in the industry, everybody thought the last column, they don't react. And then, I don't know how many years ago, a very clever, smart chemist found a way to make the inert gases react. And once you can make them react, well, they're not inert. They're pretty unreactive, though. And the name was changed to noble gases. Now, the octet rule again, in compound formation, atoms of elements lose, gain, or share electrons in such a way that their electron configuration becomes identical to that of the noble gas nearest to them in the periodic table. And that really means they obtain, by either losing, gaining, or sharing, 8 valence electrons. Click, switches off. I'll never ask you what the octet rule is on a quiz, test, or I don't think they even ask you on the final, but you have to know how to use it, which we'll be learning about in this chapter and the next. Now, when we talk about The octet rule, notice it say atoms of elements can lose or gain or share electrons. What does that mean? Well, let's find out. Let's talk about positive ions. In ionic bonding, you have to transfer one or more electrons from one atom or group of atoms to another atom or group of atoms. And when you transfer an electron or electrons, when an element loses one or more electrons, an element with a positive charge is formed. And that's called a cation. And you should know that element, when it loses electrons, forms a positive charge ion, which we call a cation. Well, what cations are formed? Well, let's look at, here I have magnesium. Let's go to my whiteboard because this will be better for you. Hang in there while I write this. If we were in a classroom, you'd be watching me write on the board. Now, the question is 3 points each, and there'll be multiple choice, not choice, multiple parts. What ion does the following element form? And the first one is magnesium. And the first thing you have to know is what's the chemical symbol for magnesium? It's Mg. Then we have to go to our periodic table. Here's Mg to find out how many protons and electrons this has. And notice magnesium has 12 electrons and 12 protons. And one of the things I found taking many tests before I got my PhD degree is let the paper do the thinking. So I'll write this down as 12 protons and 12 electrons. But what ion does it go to? Well, how do we figure that out? Well, it wants to have the same number of electrons as the nearest noble gas is that's numerically nearest. So if we look at our periodic table, here we have magnesium at 12. What are the two nearest noble gases? Argon at 18, neon at 10. Which one is closer numerically? Well, neon is only 2 away, and argon, 18 minus 12, 6 away. Now it's hard math time. Which is a smaller number, 2 or 6? Hopefully I'll pick 2. So magnesium wants to have the same number of valence electrons or electrons in total as the nearest noble gas, which is neon, 10. Remember, the atomic number tells you how many electrons. So what do? We go back and we say the number of protons will not change. However, this will now have 10 electrons. Now, to find what ion is formed, you have to remember each proton has a +1 charge. Each electron has a -1 charge. And now do the math. +1 times 12 is +12. -1 times 10 is -10. I'll add the two together. Plus 12 minus 10 gives me a plus 2. And now to show the ion, you write it chemical symbol, then to the right superscript the charge. Now the old way, which I still like to use, is this, plus 2. In your book and other books nowadays, they do the newer way, which I don't like, 2 plus. On a test, you can do either. Again, on a test, you can either do it my older way or the newer way. But in class, most likely I'll be doing it this way. So what ion does magnesium form? A plus 2. Now let's try this again with sodium. And sodium is an important element in our life. When a doctor tells you get your sodium level down, that's because it's causing your high blood pressure to go too high. Trust me, a number of years ago, I was told that. All right, how do we do this? First of all, and there are other ways to do it also, but this is the way that I found most students get this question correctly the most time, which is why I'm teaching it this way. First of all, find a chemical symbol, sodium. Remember, we're talking about electrons and protons, not valence electrons. And therefore, how many electrons and protons does sodium have? 11. Well, I'm going to let the paper do my thinking. And sodium has 11 protons, 11 electrons. But what ion does it want to form? Well, we have to go back to our periodic table. And here's sodium at 11. What's the nearest noble gas? Because it wants to have the same number of electrons as that nearest noble gas, which will also give it 8 valence electrons, which makes it stable. Nearest means nearest numerically. You have two choices. Neon is at 10, and once again, argon is at 18. Neon numerically is 1 away, and argon, 18 minus 11, is 7 away, which is the smaller number, 1 or 7. And time's up. Hopefully all pick 1. So sodium wants to form the same number of, have the same number of electrons as neon, 10. Remember, atomic number tells you how many electrons. Therefore, the protons do not change, but to form the ion, it will lose 1 electron to have 10 electrons. Now, let's do some math. 11, hold on, I see a question. And the answer is, Anna, yes, because those are the most stable. An octet, 8 valence electrons, are the most stable conformation of an element.
Okay, thank you.
You're welcome. And now each proton has a +1 charge. Each electron has a -1 charge. So we'll do the math. 11 times +1 is +11. 10 times -1 is -10. We'll add them together, and that gives us a +1. Now, when it's a +1 or -1, you don't show the number, but if you did on my test, I wouldn't care. But you just show this, and that's the answer. It forms a +1 cation. And when they're talking about sodium in your blood or body, They're not talking about sodium element, which is a metal. They're talking about the sodium cation. Now, one interesting feature of all this is when you know what cation one element in a column family forms, you know the other. And let's see if I'm telling you the truth. Let's do calcium. Calcium has how many electrons, how many protons? 20. How do we know that? From the periodic table, the atomic number equals number of electrons and protons. Oh, see, calcium. And I think I just forgot the number. Yep, I had it wrong. "20 protons, 20 electrons." Now, what ion will calcium form? Well, if you do it the longer way, because you don't know the other family member ion form, well, look at calcium. Does everybody see calcium here is at 20? And you have two choices, the nearest noble gases that are numerically close to it. 18, 2 away, and which is argon, and krypton is at 36, 20, 36 minus 20 is 16, which is smaller number, 2 or 16. Hopefully I'll pick 2. So calcium will lose electrons to have the same number of electrons as argon, which is 18. So it will still have 20 protons, but it will now have 18 electrons. And now to find the ion, we'll have to do some math. Each proton is a +1, and there are 20 of them. There are 18 electrons, each one is a -1. 20 times +1 plus 20. 18 times -1 minus 18. Add them together and you get a +2. So calcium forms a +2, which I can write that way or this way. Now, if you notice, magnesium forms a +2, and I wasn't lying to you. Once you know one member of the family, you know them all. Magnesium formed a +2. Now calcium has formed a +2. Now, how many of you have heard calcium is good for strong bones in your body, especially when you get older, so you don't get a very debilitating disease, osteoporosis? Have you ever seen people walk around like this or even have a hump back here? It's sad. And so I wouldn't get that. If you notice, I'm not a spring chicken anymore. For many years now, I've been taking calcium supplement because I don't drink that much milk and I'm not a big cheese eater. So I get my calcium not from my tea. Well, vitamin D is another issue. I'm a chemist, not a medical doctor, so you'd have to look it up. There are other vitamins I take to help me out also, but let's talk about calcium. So calcium is an alkaline earth metal. Do I have anything metal around? Oh, my ring. Hear that? This is hard. It's a metal. It's solid. Do you want to chew on calcium metal like a bar of steel? No, you'll ruin your teeth and it won't help you. What really they're talking about is to have strong bones, strong bones, and you need calcium cations, the +2. And the way you get it, thumbs up, people. Everybody see the Wikipedia entry on your screen for calcium citrate? Thank you, Anna and Jasmine. All right. Do you notice over on the right here, it shows the structure of what calcium citrate is. And thank you, Brianna, too. And the thing you should notice is when you take calcium citrate, what that does when you consume it, take the pill, which I take every morning, is you're taking something that has Ca2 plus or Ca+2, that's the calcium cation. So whenever you're taking something fortified with calcium, it's not the metal, it's the cation. And as we'll learn throughout the semester, cations and anions play an important role in our daily life. Example, calcium cations help make stronger bones. Now, how that does it, I have no idea. I'm an organic chemist, not a medical doctor, but it does, and I believe medical science. Now, if I look at the clock, it's just about time. Let's take a 5-minute break right now, some seconds away from 9:50. Come back at 9:55, and we'll do an exciting lab. So I'll see you in 5 minutes. I'm going to take a 5-minute break. Just get up and stretch. Let's get going. Give me a minute while I open up two files, because it's lab time. All right, it's lab time. Now, today's lab deals with measurements and uncertainty. Let me make this a little smaller. And what you'll be doing today is investigating when you measure something, what kind of accuracy you have, what kind of uncertainty in the measurements you obtain. And you'll be doing this with glassware and measuring volume of things. Now, the file I now have open, you can download from the assignment area of Blackboard. And what you'll need is the following equipment. You'll need goggles. You should wear gloves. You should wear your apron. Even though you're only working with water today, even when we're face to face in the lab, like last spring, I taught a class lab at COD, and this actually two labs, and this last summer. And even if the students were working with this water, they wore gloves, so did Dr. White. We wore our goggles. And luckily, the kit you have gives you an apron, but in the lab, we didn't have aprons unless the students brought their own, because we didn't use lab kits. We had the supplies. So let's look at some equipment you will need for today's lab. The first one is a balance. If you look in your chem kit, you'll find a box like this. You'll have this balance with two batteries. I did, you should. And each battery goes on this side. This opens up like this. Make sure you follow the polarity. The plus side goes on this side, the minus side where the spring is. It's hard to do this while you're looking at a camera. This part comes off, and you have a really nice balance. And I mean that. I tested it. Being a chemist, I have at home, I purchased on eBay a long time ago, a standards kit, a weights that you can check balances. And I checked this, and it's pretty accurate. I was shocked. Now, you'll have to turn this on, and then you'll wait a little while. If you see all eights, I think it wants to be put down. And now it took a little while. Now it's reading numbers. Let me zero it. It's because I'm holding it like this, it's bouncing around, but you'll see all zeros. Now on here, right here, there's a button called tare. and that's to set it to 0, which you'll be using. Now, there's a button for mode. If up here you see the letter G, you're in grams and you don't have to touch this button. If you look on the inside here, they have instructions how to calibrate. Ignore that. The balance is essentially right now, the one I got, spot on. And so it's fine. Now, when you use this balance, you'll want it on a flat, hard surface. When you, not my hand, but I'm just pretending this is a countertop. You'll want it on a flat surface. I'm going to shut it off for now. You'll also need some cups, and you have your grease pencil. In your kit, the main bag, you'll have 2 graduated cylinders. That's what these are called. You've already used it. You'll have your thermometer that's in this tube. Remember, be careful. This is glass and it can break. You don't want to break it. And I taught you last time how to use the thermometer. You'll need this large plastic beaker. And another thing you'll need, isn't this cute? It's an Erlenmeyer flask. It's named after the chemist who invented it. This is glass. Be careful, it can break. And one other thing I'd recommend that'll make your life easier, it's in the kit, an eyedropper. So that's the equipment. Again, you should wear, since I have no chemicals, I'm not using any, you should wear safety goggles, I would, gloves, and your apron. Now, what you're going to be doing is measuring liquids, and that liquid is water. Now, I've already shown you once before, but let's look at figure 1. When you're measuring water, water doesn't stay flat across. It forms this U. See how the dark blue is like a letter U? That's called a meniscus. And the very bottom of the meniscus is where you measure. Now, on this graduated cylinder, notice you have 6 and 7. That's 6 milliliters, and 7 milliliters. And if you look at what they have here, notice it's between 6 and 7. Each one of these markings between then, those 6 and 7, are 1/10 of a milliliter. So if I count 1, 2, 3, 4 in this line here, the larger one is 5.5, 0.6, 0.7. Now notice the U is right on the line with the 0.7. Therefore, I can get 3 significant figures, and the volume as seen in this picture, I would say 6.70. Again, each one of these is 1/10 of a milliliter, therefore 6. Then it's 0.7, because it's right on the line, is 0. So it'd be 6.70, 3 significant figures. Now, what if it's in between those 2 lines? Then I'd guess and say, oh, it's about halfway between the 2. Then I'd call it 6.75 if it was a little higher. And that's how you read it. Now, when you have larger ones, you have less accuracy. Maybe you'll find out. But you still look for it and guess for the last measurement. Now, when we're talking about it, there's accuracy and precision. Accuracy is how close a set of data is to the actual value, and precision refers to how close a data point is to other measurements. Now, here they talk about relative error and they show you how to calculate it, and also percent error, how to calculate that. And I'll let you read that on your own. Now, there's different types of errors. One is systematic, which is inaccuracy, a measurement to be inaccurate caused by a value in a particular direction. Example, if your clock is always it's set 5 minutes behind the actual time, you're always going to be 5 minutes late. And that's a systematic error. Now, a relative error is the more common error we deal with, is built-in percent error, like in a speedometer of your car. It may say you're going 100 miles an hour, but there's a plus or minus 2%, which in that case would be, you could be going 98, 100, or 102. And they show you how to calculate the relative error based on what it should be and what it is, divided by what it should be, for the actual, what it should be. Now, random error can be corrected. Random error is present in all measurements. And that's what you're going to be looking at. And this is called uncertainty. And you'll be measuring differences using different types of measuring equipment to see what kind of error you get. And error, over here they say, is an uncertainty is a concept we use significant figures. The more significant figures you have for a number, the more accurate it is. And the smaller the uncertainty limit is. Now, let's look at what you're going to do. You're going to use the scale, the 10 milliliter graduated cylinder, 50, the Erlenmeyer flask, the beaker, and plastic cups, and a thermometer. And what are you going to do? You're going to take your balance, make sure you press the tare button, and it reads 0.00. If there's a lot of airflow around where you're doing this, the last number might jump up and down a little. Take 2 of your plastic cups, label them with your grease pencil, 1 and 2. And what you're going to do is place your first plastic cup on the balance, but first zero it, and then record the data. Remove it, wait until it comes to 0 again, 0.0. You may have to tare it, you really shouldn't. And then you'll put it on there and measure the weight. And you'll do that 4 additional times. You'll do the same thing with the second cup. Again, put it on the balance, zero it, put it on the balance, weigh it, take it off, zero it, do it again. Now, if we look in the lab report, which is also in the assignment area, you'll be putting data in here. And here, you'll have each time you put it on for a total of 5 times, what's the weight in grams? And you'll measure what's the average, the deviation from the average. And first you'll do the average, then you'll calculate the deviation. You'll do the same thing for the second cup. Now, they should be pretty close together, but all 5 should not be identical. Maybe they will, I don't know. But at this point, you'll find out, and you'll do that twice. And there's some questions here you'll answer also. All right, let's look at the second part. All right, and asks, how do we do deviation? If you look right here on page 8 of your lab report, the deviation average is the average mass of the cup minus the mass of the cup for each measurement. And to determine the deviation from average this is an uncertainty. So let's say you have the average mass of 22.05, and then you had one that was 22.1. You do the subtraction. Now, let me point out, notice this is equal to, and they have a line here and a line after the word trial. These two lines tell you do the absolute value. And let's take a look at what that means. What's the value of this? Well, the absolute value minus 1 is 1. If you had 1, that's 1. In other words, if there's a minus sign there, you ignore it, or you absolute it, it's called, I think. I haven't used this terminology in a while. Let's try another one. What's the absolute value of minus 15? And these two lines mean absolute value. And therefore, whatever in there, you take the positive number, 15. And that's how, using the equation I just showed you, which is not just a subtraction, but an absolute value. Does that help, Anna?
Yeah, I just don't know what mass of the cup do I have
Well, you
to
got to
do, like,
measure it.
yeah, but I have 5, right? I
All right,
measure
let's
5
go
times.
back to
So
the
do I do-
data. Hold on. You're going to take, let's call this cup number 1, put it on the balance, measure it, put it in
Mhm.
trial 1, take it off, put it back on, and you'll do that
Mhm.
5 times. Now, do you know
Yes.
how to do an average?
Yes, so I have to just put
You
everything
average,
together.
add the 5 numbers and divide by 5.
Mhm.
Then each deviation will be this average minus the mass of the cup.
Okay.
And it's the absolute value, not just the value. You won't get a negative number. They'll always be positive, okay?
Okay, what about if I have like decimal?
Well, it's the same thing here.
Okay.
Let's say your average is 10.80, and I'm just making up numbers, and one of your reading is 10.20. The difference is 0.20 or 6. Get my calculator out. Hold on. Let me make these larger so you know it's not a number. And therefore, the number would be 0.60. Now, what if you have this? Now here, the number you would get inside the absolute would be 0.20. But because it's absolute, this would be 0.20. Does that help?
Yes, it's perfect. Thank you.
Okay. Well, anyways, that's the first part. Now, the second part, let's go to that, deals with uncertainty of common glassware. In other words, how accurate is the measurement based on the type of measuring device you're using. And the same thing for uncertainty, high value minus low value divided by 2 for uncertainty. Now, what you're going to do is for each one, you're going to take and turn on your balance and stabilize it or tear it. Then for each one, the first one, you'll take the 10 milliliter graduated cylinder and put it on there and get a weight. And if you notice in table 2, 10 milliliter graduate, first you'll do mass of the empty graduated cylinder. Next, you'll put in approximately 7 milliliters of water. And you'll record the volume based on what you read. And you're probably not going to get 7.00. You're a little over or under, that's all right. But read it just like I showed you. You should be able to get 3 significant figures. And you'll record it right here, where it says estimated volume. Now, you also will take and put that same graduated cylinder with the water in there on the balance. And you'll weigh it. And the mass of the water is the mass of the glass with the water minus the mass of the empty glassware. Now, the high and low value interval, you can look by looking at what's the line above, what's the line below. Say if you're at 6.6 and 6.7, and you were right at halfway between, you'd put 6.6, 6.7, 0. And you'd measure the difference would be your uncertainty. Now, we're not done. First of all, let's talk about the others. You're going to do the same thing, but with a different amount of water in each one. And how do you know what amount you put in? If you look at table 1 on page 7, notice for the 10 milliliter graduated cylinder, we put in 7 milliliters. For the 50, you'll put in approximately 24. For the Erlenmeyer, you'll do 17. And for the beaker, the big plastic beaker, you'll put in 35 milliliters. And each one, you'll take the empty glass measuring device before you put the water in there. And you will then get the weight, then put in the amount of water they tell you, like for the graduated cylinder, 50 milliliter, you'll put in 24 milliliters, you'll weigh it again. And you'll do that for each of these. Now, one thing I do need to show you, hold on, let's get back to that. For the 25 milliliter Erlenmeyer, they have 17 milliliters. Can everybody see the numbers here? Right here, it says 12.5, and right here, it has 25. Well, how do you get 17? Well, it's approximately halfway between. And your uncertainty, 25 minus 12.5, which is quite big, because you're guessing where it is. Now, once you get those numbers to see how accurate you really did, you'll measure the temperature of the room, and you'll use their thermometer. Just take it out of the case, let it sit in a room while you're doing this experiment, come back and look at the temperature. Now, based on the temperature and you should be able to get 3 significant figures from your thermometer. The density at 18.0 is 0.9986. If you're at 18.1, it's also the same. And if you go different temperatures, you can see this. If you had 20.5, here's 20, come over to 0.5, and the density is 0.9981. Why am I talking about density? Density is mass, or volume equals mass divided by density. So from your table, this table, you'll have the mass of the water. And down here, you can rewrite the mass of the water, like for the 10 milliliter graduated cylinder. You'll put down the current temperature and then the density based on that chart I just showed you, and the calculated volume of water. Remember, the calculated volume is right here, the mass divided by the density. Don't forget to use proper significant figures. And then you can check, what did you calculate? And what did you think you measured right up here? And you can see how accurate your measurement was. And that's today's lab. Now, it's very important to know accuracy. And when I managed a quality control lab, it was important to know that I could trust, and our company could trust, and more importantly, our customers can trust values for certain measurements we took for our company's products. And that's the errors. Now, Anna asked about the questions. That's a good question. Throughout the lab report, which is named in the assignment area, a number 580352, measurements uncertainty lab report. I have it both as a PDF file and as a Word document. All the questions throughout here, please answer. I think there are only 3 of them, but don't forget, like on question 3, it asks not only which piece of glassware has the highest degree of accuracy, but also why. I would have phrased it slightly different. What is the reason that has the highest accuracy? It's the same question, but it's easier to answer. So you'll just have 3 questions, and that's it. And with that, let me remind you, there'll be a change in how I'll be giving tests in the final in this course due to issues raised by a certain student. I put out announcements this morning. Today and tomorrow, I'm going to be working on how do I accomplish what I have to do, and I'll get that word out for you. If you took test number 1, I'm debating how to handle that. And with that, I'm done for today. And I'll say, Gehen gesund. Goodbye. Don't forget, if you have questions, come to my office hour tomorrow, Wednesday. With that, bye. Gehen gesund.